Now let's talk about how you actually set up a detector to make measurements. The first thing you need to make qualitative measurements is an energy calibration. The relationship between channel number and an MCA and gamma ray energy is essentially linear. Therefore, using a calibration source with at least 2 good gamma lines of known energy, we can generate an energy calibration for the spectrum. Depending on what we're trying to measure, if a calibration standard is not available, you may be able to calibrate the spectrum based on some knowledge of common peaks in the source spectrum itself. We'll see this when we measure uranium samples. Here is a spectrum taken with using sodium iodide detector with a cesium-137 source. On the right is a schematic of the decay scheme for cesium-137. We love cesium because it has about the simplest decay scheme of any isotope. Cesium beta decays to barium-137 metastable, which then emits a single 662 keV photon. Looking at the collected spectrum, here is the 662 keV photopeak, whose center is arbitrarily set to channel 100 of the MCA. We can locate the Compton edge at 487 keV and channel 71, and we can see a faint backscatter peak at about 184 keV. Here's a cobalt-60 spectrum. The decay scheme is shown on the right. Cobalt-60 decays to nickel-60 in a very high metastable state, which de-excites by emitting 2 gamma rays, one at 1.17 MeV and one at 1.33 MeV. We can locate the 2 photo peaks for the 1.17 MeV gamma and the 1.33 MeV gamma, and we can locate their associated Compton edges. Here we see the Compton continuum, we see a small backscatter peak, and we see a 75 keV lead X-ray. Above the photo peaks over here, we see a region with noise from either higher gamma rays or from summing of one of the principal gammas with a Compton interaction that happened within the resolving time of the detector. And we see a sum peak where 2 of these principal gamma rays have interacted in the scintillator within the resolution time of the electronics and just summed it up. Here's a manganese-54 spectrum. And then on the right-hand side, we see the manganese-54 decays by electron capture and emits a single 835 keV gamma ray from chrome-54 metastable. Looking at the spectra, we see the photo peak at 835 keV. We can identify the Compton edge, a backscatter peak, and lead X-rays. We've shown you this because cesium, cobalt, and manganese sources are commonly used for energy calibration.